Okay, so I just needed to take a break. So here we don't have z term because z is constant, and when you take the derivative of z, it goes away. So we have, again, I took the derivative of r on the left side and derivative of u on the right side. And we get those differentials on each side. Looking at this and looking back up here, so you can see that 2r dr will be replaced by this, okay? And we already had that in this parenthesis defined as u squared. So this integral becomes u squared to the negative 3 halves. I'm trying to show all the steps. And this whole thing is going to be 2u du. So let's see what is left here. U squared to the negative 3 halves is going to be u negative 3. And this 2 is going to come out. We have another u and du. And this is going to be 2u to the negative 2 because this has a power of 1. You're just going to add them up. It becomes negative 2 and du. Okay, and this integral is very simple, right? And it's, again, as I gave you what the integral looks like, it's going to be, you're just going to use this integral here. Okay, it was u to the negative 2 du, so it's like x to the some power dx. It's similar to this, so we can use this to figure it out. Let's go back there and then do that. So what happens is then 2 times u to the, you're adding 1, like plus 1, m plus 1. So m is negative 2. M plus 1 becomes negative 1 divided by m plus 1, and it's again negative 1. And this becomes negative 2 over u, right? Because u is to the has a power of negative 1. It's gonna flip it. Okay, so let's remember what u was, and that was u square was z square plus r square, as we defined it here. And u is going to be z square plus r square to the 1/2. Okay, so you need to take the root. So this is what we're going to replace with this whole integral. Okay, that is the answer to that. Let's go back and do that. Let's go move on to that. So it's the same thing as writing this way. It's just like the 2 at the top is flipped at the bottom, and the z squared plus r squared to the 1/2 is now at the top, so that's why it has a negative sign. So, but it is really the same thing when you put things together, and with using that coefficient at the top, like this coefficient at the top as well, right here. Okay, so this is what we got so far. Since we have r, the intervals of the integral, again, is going to be from the center of the disk all the way to the edge, which is capital R. Okay, so once you do that, you are going to, like, since there's a negative sign here, first we usually do like the upper interval and then the lower one, but since there's a negative, I would probably do the lower one first, so that would make it positive, and minus the other one. But try that and then see that you should get this answer. Okay, it's really just writing r goes to 0 and then r goes to r, and taking the difference between them, and it gives you this. Because of this 2, 4 is going to go away, so that's why we have sigma 2 epsilon naught here. That z is right here, and these are just cancelled, so we don't really, because of that 0, the first term comes from the 0. And this is the equation for a charged disk. Okay, so let's get rid of those things, and this equation is given in the equation sheet, and it says that this is the electric field due to a disk. Okay, so we will do some practices of how to use this equation and manipulate it in problems. But it is not very simple equation, right? So one thing that's gonna really simplify is again thinking about a limiting factor. Okay, so kind of a specific case. What if r goes to infinity? We say r goes to infinity means it is an infinite sheet. So it's like there's no boundaries, right? It's not just a disk. It goes to infinity. So it would be an infinite sheet. When r goes to infinity, this whole thing goes to infinity, and then some number over infinity goes to 0. So this parenthesis becomes just 1, and then your E field becomes sigma over 2 epsilon naught. So this equation is such a beauty. Why would you ask? It's because look at that, it is constant. Sigma, the charge density, is constant, assuming again this is uniformly distributed, and epsilon naught is a constant. So remember in the very first case that we discussed in electric field, I drew a bunch of electric field vectors and I said we don't care about the source. All we know that the electric field is uniform because the separation was the same, the magnitude of the field lines were the same. So it could have been this infinite sheet, because if you have, like, let's say we have an infinite sheet here, let's say positively charged, this would produce an electric field like that. Any point, doesn't matter where you are. It does not depend on r. It does not depend on the distance. Here it is sigma over 2 epsilon naught. And here also it is sigma over 2 epsilon naught. And that is true for non-conducting or insulating sheet. Okay, when we have a conducting sheet, it's gonna be that 2 is gonna drop, and we will discuss that in the next chapter when we apply Gauss law to get these answers. Instead of doing really long derivations, there's a quicker way to do it, as long as the symmetry permits, and for these problems it does. So we will discuss that in next chapter. So next chapter is going to be also some derivations, but if you ask me, these derivations are harder than the others. So okay, again, this electric field is also given on the equation sheet, and you should check it. There's one for conducting, another one for non-conducting or insulating. Kind of get familiar with these equations, understand what sigma is, and realize that this is constant, not changing with distance. And you know that the point particle is changing with 1 over r squared. For example, dipole is changing with 1 over z cubed. And you can also see the charge disk also has z dependence in it, but not if it is an infinite sheet. Okay, so far we explained how the equation for the electric field on the central axis of uniformly charged ring can be used to find the equation for the electric field on the central axis of a uniformly charged disk. So we didn't repeat what we did before. And for a point on the central axis of a uniformly charged disk, we apply the relationship between the surface charge density and the disk radius r and the distance z to the point. So we got that equation.